Hello and welcome to Tonight at 8 from the RSGB. As well as conventional amateur radio, the HF radio bands can also be used to observe many interesting phenomena such as meteor trail reflections, radio blackouts, aurora reflections, sudden frequency deviations and aircraft reflections, as well as other propagation anomalies due to ionospheric patches and blobs. Well, our guest this evening is Whitham Reeve from Anchorage in Alaska, who studies this phenomena and is going to tell us more about aurora reflections. Welcome to Tonight at 8, Whit. Can you give us a brief overview of what you'll be talking about tonight?
Yeah, thank you, David. I operate a form of a bistatic radar in which I use the HF transmitters for time and frequency services that are on all the time. And then I use my receivers in Anchorage to receive reflections off of the Aurora northern part of Alaska.
Well, it sounds fascinating, and as radio amateurs, we're looking forward to finding out how you do that. And if you are watching this on Monday, the 8th of April, then this is live, and you can ask Whit questions or make comments on either YouTube chat or BATC messaging at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. So now let's go back to Whit and find out more about HF aurora reflections.
Good morning good morning from Alaska. It's probably early evening over there. Talking about the reflections in the HF band from the Aurora in northern Alaska. And my presentation will take about 1 hour. And here's the contents of which I'll be speaking. I have just a few introductory comments. We're going to look at the concepts of aurora radio reflections. And then in the second part, we'll talk about my observations of that phenomena. So here's geographically what we're looking at. I operate 3 radio observatories in Alaska, and the one that is important for this presentation is Anchorage, which is located right here in south central Alaska. And the distance scale here, it's about 300 kilometers from HARP to Anchorage. So that'll give you an idea of the distances that we're talking about for Alaska as a whole. Now, the aurora radio reflections that are discussed here were taken at Anchorage, and Anchorage is just at the southern edge of the auroral oval and at 62 degrees north magnetic latitude. And in these observatories, I look at a lot of different things, aurora radio being one of them, meteor trail. I also operate geomagnetometers at these sites. I do a lot of high latitude radio propagation studies and things like that. Now, what is aurora radio reflections? Well, you may have heard a lot of different terms that are used to describe the same phenomena. Radio aurora, aurora radio, aurora scattering, aurora echoes, aurora reflections. These all mean exactly the same thing, but they're not to be confused with radio emissions from aurora. And those are usually at very low frequencies, and they're called aurora kilometric emissions or aurora kilometric radiation. So these are reflections and not emissions from the aurora. This image here on the right is an artistic representation of a really complex phenomena. Now, we have a transmitter, which is the transmission part of the bistatic radar. It transmits up into, usually toward the north, where it encounters higher density electron clouds. And these electron clouds are formed by the particle precipitation that falls down into the upper atmosphere and increases the electron density. Now, that radio transmission from that distant transmitter are then reflected to a receiver at some different location. And that's the definition of a bistatic radar, is transmitter and receiver that are at different physical locations. So these electron clouds are aligned with the Earth's magnetic field, which at northern latitudes or at higher latitudes are almost perpendicular to the ground. And so this makes almost an ideal reflection surface for a low elevation angle transmission coming in to the electron cloud and then being reflected back to the receiver. Now, aurora radio reflections are familiar to a lot of radio amateurs, especially those that use the SAM3 magnetometer. The SAM3 has got a K-index alarm feature, which notifies of rapid magnetic field changes. When you have rapid magnetic field changes, you have a very high probability of aurora, and then in turn, you have a high probability of what is called auroral communications. Usually in the 2, 6, or 10 meter band is where this occurs. Radio amateurs will point their VHF radios, antenna beams to the north, and then they're able to communicate with people that are maybe east and west of them who are also pointing their antennas toward the north. Now, the magnetometer is also used by aurora photographers because they will get a notification and can go outside and take pictures. Now, the first indication that there was aurora effects on radio propagation were noted in publications as far back as 1926. Specifically, the QST magazine by the American Radio Relay League had published some letters to the editor and so on. First appeared in 1926, and there was then a lot of reports that followed up through that, through the 1930s and 1940s. And the U.S. Army Signal Corps then hired a consultant to look at these radio amateur publications for reports of aurora radio phenomena. And then they compared those to visible reports of visible aurora that were taken at the same time. And those studies confirmed that there was a coincidence between this so-called radio aurora and visible aurora. Now, this was then studied very seriously in the early 1950s through the 1960s, using both bistatic and monostatic radars. Now, in our configuration that we're specifically worried about in this presentation is a bistatic radar. We'll have a transmitter over here on the lower left, and it sends a signal out to a aurora reflection region, and then the signal is then reflected back to a receiver at a different location. And the geometry of this transmission and reflection is very important. This drawing that I'm showing you here is actually a two-dimensional representation of a three-dimensional phenomena. So what it means is that this transmitter, this receiver, and this reflection region all have to be in the same plane. So the plane may be tilted one way or the other. And then this angle, it has this bisector angle that you see between the incoming transmitter signal and the outgoing receiver signal or the reflected signal. That bisector then cuts that angle in half. And so the geometry is such that this reflection region is approximately 90 degrees with this bisector. So the geometry is pretty important. And if you don't have that, then you probably aren't going to receive the reflections. Now, it was found that in these early investigations that the received signals had a very high fading rate, and it was roughly proportional to frequency. And so voice communications were almost impossible using this as a type of a communication media. medium. And at 50 megahertz, the signal fading rate was as high as 200 hertz. So that made the communication, or the voice communication, really difficult. CW communication was more or less the same, didn't work very well. But that raised the question is what causes this high fading rate? And there were several explanations that were put forth. One of them is that the absorption in the ionosphere changes, and so that it changes rapidly enough where it causes this signal fading. There's also the possibility of interference between wave components that could cause the fading, and or the changes in electron density in the reflection region, or even drift movement of those columnar field-aligned electron clouds that I showed in that image earlier. Now, what probably is happening in reality is that all three of these may be taking place at the same time and causing that fading. Now, it was also found that directional antennas gave the best results when they were pointed north toward the aurora. And so this indicated there was some kind of aspect sensitivity to the phenomena. And what this means is that if there was if you had a receiver that had a beam antenna pointed, let's say to the west, you weren't going to receive anything. But if you pointed that same antenna toward the north and the geometry was correct on the incoming signal, then you would receive aurora radio reflections. And of course, like everything else in electromagnetics, there was exceptions that were observed on this effect. Now, there was no skip zones or skip effects observed in these earlier observations and investigations. And it was also found that the polarization of the received signals was not that much different than the transmitted signals. So there was a lot of very fundamental things that came out of these early studies. Now, there was another thing that came out was that even though there was a relatively high coincident rate of visible and radio aurora, you could get the aurora radio reflections when no visible aurora was present. And of course, if there was clouds, you wouldn't be seeing the visible aurora anyway, but you could still get the radio reflections. Now, another thing was that the radio aurora and geomagnetic activity were well correlated. So in other words, if there was any kind of geomagnetic storming or disturbances, then there was really a high probability of having radio aurora. And of course, this is true of visible aurora as well. Now, it was found that there was no reflections received when the aurora was directly overhead. So if you have a strong geomagnetic disturbance, the auroral oval where the aurora actually occurs is pushed toward the equator, pushed southward. And if you were far enough north where that oval was directly above you, you could not receive any aurora radio reflections. You still could receive them if your antenna was pointed to the north, but not if it was pointed straight up. And that goes back to the geometry that I showed you earlier. Now, it was also found that aurora radio reflections were strongest when the visible aurora had a ray structure to it, and the structure was close to the horizon. In other words, this was a low elevation angle type reception that was being investigated. I have to take a drink of water here. Now, it was found by using these different kinds of radars that most aurora radio reflections occurred when the visible aurora was below approximately 110 kilometers altitude. Now, it's been established for a long time that aurora will reach down to maybe 100 kilometers altitude, or maybe even slightly below that, but it can also reach as high as 700 kilometers altitude. It was also found that the visible aurora most often was distributed around local midnight, while radio aurora peaked before midnight. And that's kind of an interesting fact that came out of these investigations. Less than 1 part per million of the energy incident on the aurora was reflected back toward the receiver in these early investigations. So that implies that there was a 60 dB reduction in power. There was a 60 dB power loss in the reflected signal, which doesn't really sound like it's an important number, but that was a lot of measurements were done to see how well the aurora was a reflector. And so this 1 part per million fell out of that. Now, the reflections that were measured in those days had radial speeds of up to 1,000 meters per second. So that means that the reflection surface was moving toward or away from the receiver by up to 1,000 meters per second. It was found that most of the frequency shifts, though, were less than 600 meters per second. And in the investigations that I've done, I'll show you I was seeing maybe 200 meters per second, which falls in line with this. Now, all of the early investigations were in the VHF and UHF bands. There was none that I could find in the HF band below 30 megahertz. So that made what I was doing more or less kind of a unique part of this overall investigation. Now let's look at some of the concepts. We know that visible and radio aurora are different manifestations of the same physical process. Visible aurora is caused by atomic and molecular excitation, and that produces the light that we see from the aurora. So we have these energetic particles that are precipitating or falling down into the upper atmosphere and at high latitudes. And this induces the neutral atoms and molecules in the upper atmosphere to produce light. Now, radio aurora is caused by the ionization of atoms and molecules. So these same energetic particles that are raining down cause the neutral atoms and molecules to ionize, and then it's that ionization or electron clouds that are causing the reflections. Now, if you want to find out a little bit more about how aurora forms and so on, I put a link in the chat of a paper that I wrote that accompanies this presentation. You can download that and read through it if you want. Now, it was found that the visible and radio aurora do not necessarily occur at the same time. So having one doesn't mean you're going to have the other. But there is a high probability that you will, but it's not necessary. Now, radio aurora has been recorded at very low latitudes, all the way down to 25 degrees. So that's getting pretty close to the equator. And you'll never, ever see a visible aurora that low, or it's extremely, extremely rare. Now, a radio aurora can occur during daylight when you can't see the visible aurora. They share many characteristics in terms of geographic and height regions. They both occur at high latitudes, like where I live. I'm at 62 degrees magnetic north latitude. The phenomena occurs in the neighborhood of 100 kilometer altitudes above the ground. Well correlated with geomagnetic activity, as I mentioned earlier. They both have similar statistics of observation and motion, that is the Doppler shifting. They vary in a similar manner annually and over solar cycles. And one of the things that is notable about both radio and visible aurora is that they show 1, 2, or 3 daily variations of peak activity. So in other words, you'll have a, let's say, a burst of visible aurora. It will subside for a little while, and then it'll burst back and maybe subside again. And this cycle will repeat itself over the night. And these are called auroral substorms or geomagnetic substorms. Now, this is kind of a schematic of what is needed or what I used in these investigations. We have a transmitter, and I'm showing in this example here a transmitter in Kakaha in Hawaii, and this is a WWVH transmitter that's used for time and frequency services operated by the U.S. government, and it's on 24/7, extremely accurate in frequency and time, and it transmits a signal omnidirectional from Hawaii. And so the northward beam then goes up to the north and encounters these field-aligned high electron density regions. Now, this is higher ionization level that occurs along a magnetic field line. And at higher latitudes, these magnetic field lines are almost vertical with the ground. And then, so part of the geometry then is satisfied by having the incoming signal being at almost right angles to the magnetic field line where all these electron clouds are aligned. And so you have a reflection then from that electron cloud, and it comes back down into a receiver. And this particular, in my case, it's a receiver at Anchorage, Alaska. And the distances involved for the phenomena that I was looking at is, I believe that these reflection regions are maybe 500 to 1,000 kilometers north of Anchorage, whereas the transmitter is about 4,400 kilometers south of Anchorage. So these radio waves from the transmitter have to travel a very long distance. It's obviously going to be multi-hop or multi-mode ionospheric type propagation. And even coming back to me, the propagation has to be pretty good for it to get all the way back to my receiver in Anchorage. So this is an elevation view. This is a drawing that I would see if I was standing on the ground looking, say, to the east. And down below here, I have another drawing that would be if you were standing, you were above at a high altitude above the Earth. And you can see the transmitter is down here in the very lower right-hand side. And it goes up to a reflection point in the ionosphere north of Anchorage, and then is reflected back to Anchorage here. So these angles all have to be just right, both in the overhead as well as the elevation view here. And as long as you have that geometry and or very close to it, then you're almost assured you're going to receive these reflections. Now, one of the problems that I had trying to figure out what was going on here is that because of these distances, what kind of propagation modes were taking place? Well, first of all, we have this bistatic radar with transmitter and receiver at different fixed locations. They're separated by some distance, in my case, over 4,000 kilometers from the transmitter to my receiver, but in the neighborhood of maybe 5,000 kilometers from the transmitter to the reflection region. And my receivers are tuned to the WWV and WWVH frequencies. These are simultaneously transmitted by both of these stations at the same time. And so there's no real way for you to differentiate between the two other than by the voice announcements. A woman makes voice announcements for WWVH in Hawaii, and a man makes the announcements for WWV in Colorado. But look at the geometry here. The station in Hawaii is almost exactly south of Anchorage, whereas the station in Colorado is almost exactly east of Anchorage. So the geometry for or the idea that you have to have your antenna pointed north in order to receive these reflections indicates that WWVH is more than likely the station that I was receiving. Here's a map that shows what I think the geometry is. Here we have the station down here in Hawaii, and it's going almost exactly north to Anchorage, but the radio waves are going to continue on, and the reflection region, I believe, is in the northern part of Alaska. And it's about 1,000 kilometers from here in Anchorage to the north coast of Alaska, where I think the reflections are taking place. So we don't have the required geometry from the station in Colorado, the WWV transmitter that's shown here by this red line. So this is what I think is taking place in, at least in the reflections that I was receiving. Now, this is obviously non-line of sight. Excuse me. It's non-line of sight. It's assuredly a multi-hop or a multi-mode type propagation. So I came up with this idea of maybe these reflection points are virtual transmitters. So here's the transmitter that originates the signal, and it's refracting off the ionosphere on its way north toward Alaska. And at some point, one of these reflections, either in the ionosphere or maybe on the ground, is got the correct geometry for the Aurora over here on the far right, and the correct geometry both for the receiver and transmitter and the Aurora itself. So I call these virtual transmitters. They don't exist in reality, but that I believe that's the only thing that can be said to satisfy the overall geometry of the path. Now, one of the things about this kind of propagation where you're using the ionosphere is that you're going to have daily, seasonal, yearly, and long-term variations, and because the sun controls everything, and you know that the sun has daily variations. It varies with the season. Has the sunspot cycle, which is roughly 11-year cycle. And so you have not only the direct solar effects, but you also have daily changes due to, say, the solar terminator itself, which moves westward across the around the world as the Earth revolves. So you have all these variations that come into play when you're looking at the propagation of this setup. Now, here's the instrumentation that I use, and this is the Anchorage Observatory. In 2020, when I made these observations, I only had one HF receiver. It was an ICOM R75 connected up at that time. I have since added a couple R8600 to the mix, and so I'm actually monitoring 3 frequencies now in the propagation studies that I do. And I had have a receiver multi-coupler here on the RF input to the receiver, so that I have a single antenna, which is a 8-element log periodic dipole array, design frequency range of 18 to 32 megahertz on a rotator. And that single output, or that output from that single antenna, then is split into 8 ports. And conceivably, I can connect up 8 receivers, and sometimes I do have as many as 8 receivers going. Now, the audio outputs from these receivers goes through a 6-port audio mixer to a line-in port on a PC, and I run Argo software that produces an image every 12 or 13 minutes or so that shows a narrowband horizontal waterfall of the audio output from these receivers. And I'll show you more of that in a minute. Now, to support all of this receiver setup that I'm showing here, you have to have a lot more than just a receiver and maybe a coupler and an audio mixer. I have, of course, a local area network, uninterruptible power supplies, access to the internet through a WAN, wide area network. I have NTP time servers to keep the timestamps on the PCs correct. You have your power supplies. You have your control system for the rotator and so on. For these studies, the antenna was pointed, I believe, to the, if I remember correctly, it was pointed to the east, but it's a pretty broad beam type antenna. So it's not that directional at the frequencies I was looking at. Now, to make all this stuff work, I use the Argo software. And what Argo is a real-time narrowband horizontal spectra waterfall. So you have this image of the received signal, and what this image shows is a horizontal waterfall of the demodulated signal. So this is the audio output, and I tuned the R75 was tuned to 15 megahertz and up by 1 kilohertz. And so receiving the carrier from the transmitter at exactly 15 megahertz gave a 1 kilohertz tone. And so that's the 1 kilohertz tone is actually what you're seeing here on the horizontal, the white area on this plot. There's 1-minute timestamps that are produced by the software. You have a time and date that gives you a timestamp for each image that's produced, roughly 12 or 13 minutes apart. This frequency scale is the demodulated signal. It's not the carrier frequency itself. It's the demodulated signal, which for my setup was 1 kilohertz. So we'll be seeing many more of these here in just a minute. I also use a magnetometer because the magnetometer was required to know, to correlate geomagnetic disturbances with visible and radio aurora. So I use the SAM3 magnetometer here in Anchorage. I've had it in service since 2008, and it's a 3-axis unit, and it uses the same infrastructure. It's a standalone unit and produces a magnetogram shown here. Magnetograms are going to be 24 hours long, and these squiggly lines then are each of the 3 axes, east, west, north, south, and vertical. And you have this K index, which is an indication of the geomagnetic activity, where a K1 would be very quiet and K9 would be extreme magnetic disturbance. Okay, so now let's get into the observations themselves. There's what I used to go through all of these Argo images to find radio aurora was, first of all, that there was a rapid frequency variation shown on the Argo plot on timescales of seconds or minutes. And the other criteria then was the rapid variations in the magnetic field at the same time as those frequency variations. Now, all of the observations that I'm going to show you here were from 2020. I had to go through over 43,000 images, and I'm going to show you a very small fraction of those that show radio aurora. it turned out that when I took these in 2020, that was the first 12 months of the solar cycle 25, the current solar cycle that we're in right now. And I'm planning to come back and revisit this after a 5-year time period. So at the end of 2025, I'll go back and look at the year at those 43,000 images produced during 2025. And I'll make a comparison to see if there's anything that looks different or maybe correlates with the earlier observations. Now, as far as the geomagnetic aspects go, all the Aurora observations that I'm going to show here were accompanied by a geomagnetic disturbance. In fact, what happened is that one day I was kind of sitting and staring at the screen, and I just happened to have both Argo and the SAM-3 magnetogram up on the screen at the same time. And I noticed that they were moving together in terms of the radio reflections were obvious on the Argo plot, and the magnetic disturbance was obvious on the magnetogram that I was looking at. And so that is what actually caused me to realize what was going on. And it turns out that it's the rate of change of the magnetic field that was important. It wasn't the amplitude of the magnetic change that was important. It was the gradient or the rate of change of the magnetic field, and that is what led to the radio aurora. And so, in other words, storm conditions were not required. A storm generally is called with a K index of K5 is considered, anything above that is considered a magnetic storm. But I saw these variations as with a K index as low as K3, which is relatively quiet. Now, there was the variability pattern was very similar to what you see with visible aurora. You have a relatively quiet condition. It changes to an active condition. And if it's visible, it'll be brighter or more active, and then it returns to a quiet condition. And this may happen 1, 2, or 3 times a night when there's when aurora is active, and those are called substorms. Now, the audio, when I would listen to this, it was the audio had rapid variations. There was a flutter or a stutter, a rapid hash or buzz-like sound. It was always very weak. In other words, the reflections were always very, very weak. And sometimes I couldn't tell which source was the transmission source for the reflections. But as I pointed out earlier, they were very unlikely to be from WWV in Colorado, which is east of Anchorage. Now, sometimes I could hear a female voice, and that told me, yes, this is WWVH. Sometimes I could hear a male voice. What that tells me is that I was probably not, when I was hearing a voice, I probably was not hearing the reflection itself. I was receiving or hearing the direct path from the transmitter directly to my receiver, and it was not reflected. So, and I'll show you some examples of that here in just a minute. Most detections that I saw were in the dusk to midnight sector. So this would have been after sunset, but before midnight. And so here's a drawing of the Earth over here on the right. I'm above the North Pole looking down. And so the sun would be off to the right, and the Earth is orbiting around the sun by going down. And so the dawn would be over here. The dusk would be here. This would be near sunset. And so my observations that I saw were mostly in this region here, dusk to midnight. Now, I did have a few daylight detections. And so it turned out that the propagation geometry was just right at those times. Now, I saw two types of spectral signatures in that Argo plot. I would see bright, thin traces, rapid frequency shifts. Often they covered the full frequency span of the Argo plot, which was plus or minus 20 hertz. And I called that discrete Aurora radio. And then I also would see bright but diffuse traces that had rapidly drifting frequencies. And I called that diffuse Aurora. The diffuse Aurora did not have the frequency variations or as high of frequency variations as the discrete. Some plots that I'll show you here in a minute have both types, both discrete and diffuse Aurora, but they don't occur simultaneously. In other words, they're not on top of each other on a plot. The Doppler frequency shift that I would see was up to 20 plus or minus 20 hertz. Now that was limited by the Argo software setting. So if there had been higher frequency shifting, then they would have been off the plot and I would not have seen them. This rate corresponds to a radial velocity of a few hundred meters per second. So that means that the reflection region was moving toward or away from the transmitter and receiver by a couple hundred meters per second. Okay, so here's one of the first plots that I'll show you, and this shows a quiet, active, quiet sequence. The plot down here at the bottom is several Argo plots that I've spliced together. And this was in January 2020 at about 0700 UTC. And so this whole plot is 48 minutes long. You can see that it's fairly quiet or inactive over here on the left, gets quite active in the middle, and then tapers off again to quiet. And this corresponds exactly with the time shown on the magnetogram up here at the top. So 0700 would be about starting right here. And you can see that it became quite active after that. And that corresponds exactly with this activity that you see here. So this would be called a diffuse aurora here, because it's a fairly thick, bright line. These lines that you see, these faint traces that are almost vertical, those are spurious signals. Here's another one that shows a double path. And by double path, I mean that I was receiving reflections from probably two different regions in northern Alaska. You can see one here, it's quiet over on the left, and then it brightens up on this trace. But meanwhile, there's another trace that comes into play here, and this is from a separate reflection region. It could be a reflection region that's nearby. It could be several hundred kilometers away. The time on this is about 1000 UTC, which corresponds to this little blip that you see right here. So there was a rapid change, and not very much, but it was rapid in the magnetic field shown on the magnetogram here, and that corresponds exactly with what you see down here, down below. Here's an example of discrete and diffuse aurora on one plot. You notice that they are not really overlaid. There is a little bit of overlay, but here's the discrete aurora over here on the left-hand side. This is an 80-minute plot where I've spliced several Argo images together. So here's your discrete aurora over here on the left, and then it morphs into a diffuse type aurora shown on the right part of this graph. And this was starting at 0600 through 0720 UTC. And so that corresponds with this activity that you see in the magnetogram right up here. Here's an example of discrete and direct path. So what I mean by direct path is that there was I was receiving the transmissions from the transmitter, which I think was in Hawaii. So this would have been from directly from the transmitter in Hawaii to my receiver in Anchorage, and that's indicated by this straight horizontal line that extends all the way across this plot. But superposed on this are discrete aurora, and that's shown by these really rapid variations that you see scattered throughout the plot. Now, this signal that you see here is fairly weak. This, I'm not sure if that's aurora or if that's just a spurious signal that's drifting through the passband of this image. It could be one or the other. I'm not real sure about that. The time on this is 0600, so that would correspond to this region here on the magnetogram. Here's some daytime aurora. This was on the 2nd of June in 2020 at about 0400 UTC. So that would have been, about 7 o'clock in the evening. So we're still several hours from sunset in Anchorage in June. And so you can see that there's probably some direct path here shown by the horizontal feature. But then this is the aurora reflections that you see over here. There's some here as well. You can see some over here on the far right. The time 0351, so roughly 0400, that would put it in this region right in here on the magnetogram. Now here's a substorm. And this is a really good example of this going from quiet to active to quiet and back to active again. So this middle Argo plot that you see here ends at this point. The one just below it starts at that point. So you can see there's a little bit of activity over here on the far left, but it then is really quiet. There's no reflections received. There's nothing received at all during this time period here. And then it lights up again and extends down to the lower plot. And so you can see that it's fairly active, but then it tapers off, gets quiet, but comes back to life. And you see the bright traces here, and then it starts to taper off again. So this is a good example of a substorm. The time period is 0545 through 0838. So that would correspond to this time period right here shown on this Argo, on the magnetogram above. Okay, so those are a tiny fraction of the observations. And there's a little bit of discussion or maybe even some conclusions from this. One is that the transmissions were very likely from WWVH in Hawaii, just because the geometry works out for that and didn't work out for any other, for the other time frequency service station. And I believe that the reflections originated close to the northern horizon. That would be an elevation angle of maybe 1 to 4 degrees, corresponding to distances up to about 1,000 kilometers north of Anchorage. And that puts it up to the very top of Alaska at, I think the latitude up there is 71 degrees magnetic north. The detection times, in my case, they were almost all of them were before local solar midnight. And there was a few that I detected from the midnight to dawn sector. There was a few that I detected during daylight hours. So one of the main things that came out of this is that the auroral radio detection at Anchorage depends on the HF propagation conditions, not only from the transmitter to the aurora where it's reflected back to my receiver, but also from the reflection region back to my receiver. So you have to have the proper propagation conditions for a very long distance coming up, and then a moderate distance coming back from there to my receiver. There are some other things that came out of this, is that there was some conclusions from the early investigations that were consistent with what I was seeing. So that's always a good sign that you're able to correlate what you're seeing with work that someone else has done. In this case, the work had been done in the 50s and 1960s. And so whatever they found is still true today, which is what you would expect for any physical phenomena. There was some other results that they had in the early days that didn't correlate exactly with what I was seeing. And so this is worthy of more investigation to try to resolve those differences. Could be because of the way I had my receivers set up in lower sideband mode versus some other mode that maybe was used in earlier investigations. Another real strong observation is that it was the gradient or the rate of change of the magnetic field that was important. It wasn't the magnitude of the change in the magnetic field, it was the slope or the gradient of the change that I found to be important. So that's it. And just to remind you, what I just spent almost an hour talking about is we have a transmitter that sends a signal out. It goes northward to a reflection region in the aurora where the electron density is fairly high, and it's reflected then to back down to a receiver at a different physical location. And what's important here is that these magnetic field lines are almost vertical, which they are in northern Alaska. They're within a few degrees of being almost perfectly vertical. So it's almost an ideal reflection type propagation geometry for doing these kinds of studies at high latitudes. So that's pretty much all I have. I mentioned earlier that there's a paper that goes along with this. I put the address for that in the chat. So if you're interested in pursuing this, I cover all of these aspects in far more painful detail than I just gave you over the last 50 minutes or so. So that's all I have, and thank you for listening.
Thank you very much, Whit. What a subject. It's obviously, as you will know, propagation of radio waves is, no matter how good our stations, we're so reliant on that. So this is a subject which will interest many radio amateurs. And if you've got any questions or comments you'd like to share and haven't already done so, please do it now on either YouTube chat or BATC messaging. And please don't forget to include your first name and your call sign if you have one. We have got a couple of questions already, which I'll read you in a moment. But first, we just actually saw on that last slide a little bit of background. I was wondering why you're doing this and what was your background. And I read on there that you've been an electronic engineer for 40 years. So maybe can you just contextualize why you've done this research?
I've always been interested in propagation, dating back to the 60s. And it didn't take me long. I've lived in Alaska all my life, and it didn't take me long to realize that radio propagation at high latitudes, i.e., that is Alaska, was much different than what I was reading about at lower latitudes. So I just got interested in it, and when I retired my engineering firm back in 2009, I decided that I wanted to pursue some of these things that have been bothering me for the previous 50 years or so. So that kind of led me to do this, and it's a fun way to use your knowledge, or the knowledge that I had gained while actually working for a living. It was a fun way to leverage that into something useful that's just fun to do.
And it's a very good reason for doing it as well. I will honestly get to your questions at home. Just one other, just follow up to that though. Have you ever thought of becoming a radio amateur because of your interest in radio waves and propagation?
Yeah, I worked in radio engineering virtually all my life, and I've thought about it, but I have never actually pursued it.
Okay, all right. Well, that's honest. Thank you very much, Whit. So let's get to some of your questions now. And if you have got any questions or comments, please do ask them now. So first one is from Terence 2E0IPK, who says, thanks for the lecture. Very interesting subject. How much effect does Aurora have on HF in regards of distance and S points? That's how we measure our levels, as you probably know. And would it make for a noisy band?
I didn't notice any difference in noise. It was really the reflections that I received were so weak that you could say that the signal to noise ratio was very close to 0 dB. So I didn't notice any increase in noise during these periods at all, but I really wasn't looking to measure that aspect of it. I was more interested in detecting the reflections more than any background noise associated with it.
Okay, well, thank you very much. Next question comes from Martin G3ZAY. Is there any advantage in beaming north and using antenna directionality to reduce direct path signals?
I don't think, if you're interested in communication, I would say that using aurora reflections is probably not the way to go. It's the geometry is similar to meteor trail reflection, which can be used for communication, or at least short communications. But the aurora itself, for one thing, the variations are too rapid. The received signal, at least in my case, was too weak to even be able to discern a voice. So I don't think it would really work in the HF band.
Okay, thank you. Another question now from Steve M1SDH. When seeing discrete and direct path, would that be similar to monostatic, as hot point is close to your receiver, brackets virtual transmitter? Therefore, would you expect an echo if you transmitted?
You know, the transmitter was over 4,000 kilometers away, so I wouldn't call that monostatic, but maybe I misunderstood the question. But in my case, the transmitter was so far away, the direct path. Well, I think the fact that I received it was more coincidence than anything else, because it was really the reflections that I was looking at, and it was kind of surprised me whenever I would receive a direct path and actually hear the voice transmissions.
Yes, I think looking at his question, I've got the advantage of looking at it again, and he says, would it be similar to monostatic? I think that was so in other words, he's making a comparison between the two.
Oh, okay. Yeah, I guess I don't think it would be.
Okay. Well, that's got through our questions, I think. Oh, no, just a follow-up, sorry, from Martin G3ZAY. Just a follow-up. He says, I was thinking more of getting a clearer view of the reflected signals rather than using the reflections as a primary communication mode. He's the person who asked the last question but one. So does that help with that? He's the one who asked if there was an advantage in beaming north.
Boy. I don't know. I guess I don't know if there would be any advantage.
No, and it's a difficult subject, isn't it? Because over the excuse me, over the years we've had many discussions on here and other platforms, and obviously in Radcom and magazines about propagation, and it's obviously still a lot to learn from this. So it's a very broad subject, but thanks for bringing it tonight. I think it would be remiss of me if I didn't mention something, though, that isn't what you're here to talk about. But while we've been on air, in fact, there's been a total eclipse in many parts of the world. So I just wondered if your research had ever gone that far and to look at the effects of propagation on something like a solar eclipse, as many parts of the world have seen today.
Yes, that's really interesting, because on last Friday, I gave a presentation about the same time of day to the radio astronomy group at the British Astronomical Association on that very subject. We had an eclipse in October of 2023 that crossed the US, and I set up a bunch of VLF as well as HF receivers for that. And my presentation to them was on the VLF propagation phenomena associated with eclipses. And I also have those same receivers set up today. The eclipse, I believe, is ongoing right now, and I'm letting my receivers record all that data. So sometime within the next month or so, I hope to have a paper written on that very subject.
Oh, that's good. I'm glad I mentioned it. We hadn't mentioned it beforehand, but at least for us, it's only hit the news in the last few days, because there's not many parts of Great Britain where we can actually see it. Or even part of it. But anyway, thank you very much for answering that. And thank you very much indeed for the whole of your webinar. And we wish you luck and good fortune with all of your research in the future. And let's hope it helps us as radio amateurs understand our radio propagation a bit more. Thank you very much, Whit.
Yeah, thank you.
There we are. And that concludes this webinar. And thanks once again to Whit and Reeve. And also thanks to the team who put this series together behind the scenes. Now, we hope you've enjoyed this Tonight at 8 and that you'll be able to join us next time when Mike Willis, G0MJW, will be taking us through designing a printed circuit board with the free KiCad PCB software. A reminder that the RSGB's annual general meeting will be live online from 10 a.m. this Saturday, 13th of April. As well as the results of the elections and the formal part of the AGM, there will be an interesting review of the year by the President, the announcement of trophies and awards, as well as the winners of the RSGB construction competition. There are 3 board directors being put forward for endorsement by the members. So if you're an RSGB member, do use your vote before 9 a.m. on Thursday, 11th of April. You'll also still have a chance to ask the board a question by submitting it in advance via the web form. At the end of the AGM, there will be a presentation on the new licence conditions by Ofcom Group Director Spectrum, David Willis. Following this, there'll be a live Q&A with 4 senior representatives of the RSGB. Do take this opportunity to get involved and ask questions about how to make the most of the new conditions. To find out more, go to the RSGB website at rsgb.org/AGM. And if you'd like to see details of future webinars or watch recordings of previous programmes in this series, please visit rsgb.org/webinars, where you can also send us comments and feedback. And if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. Until next time, this is David G7ERP signing off and clear. Bye-bye.